everyone, and welcome back. You're watching the 25th lecture in the series Mathematical Methods for Economics, and this is the second part of the lecture, which is titled Techniques of Differentiation. In this part of the lecture, we're going to be talking about a very simple yet very powerful and very intuitive rule, which is the chain rule. And in this context, we will also be talking about, we'll also bring in this concept of a composite function. We will see how the generalized power rule, which we talked about in the first part of this lecture, is nothing but a special case of the chain rule. So let us start with the chain rule, and let's set things up first. And in this framework, we'll also have to bring in this concept of a composite function. So what are we talking about here? Let us suppose y is a function of u and u is a function of x. This is then to say that y is a composite function of x. What do we mean here? It's basically to say that we are composing a function, or we are building a function which is a combination of different functions. So actually what is happening here is something very interesting. Let's just untangle things a little bit, unentangle things a little bit. So we have y as a function of u, and u in turn is a function of x. So what happens is that every time there is a change in x, because u is a function of x, that will trigger off a change in u. And because y is a function of u, that change in u will then in turn trigger off a change in y. So what are we seeing here? Every time there is a change in x, that will lead to a change in y, which is routed through a change in u. And this then sets off a chain reaction. So every time there is a change in x, this sets off a chain reaction. Change in x will lead to a change in u, which in turn will lead to a change in y. So this is then the idea of a situation where y is a function of u and u is a function of x, so that y becomes a composite function of x, which is saying that delta x leads to a change in x leads to a change in y, which is routed through u. Now, the interlinkages here then can be brought in when we talk about the chain rule formally. And here we have that if y is a differentiable function of u and u is a differentiable function of x, then y is a differentiable function of x, and dy by dx then can be written as dy by du times du by dx. It's actually something very intuitive, because what we have in this formula here is nothing but a reflection of what we just said in the previous slide, which is to say that because u is a function of x, every time x changes, that will lead to a change in u. And because y is a function of u, every time u changes, y is also going to change. In fact, if you see here the way things are expressed, if I cancel the du on the right hand side, if you see here, if I cancel the du here with the du here, that gives me nothing but dy by dx. So this is a chain rule where dy by dx is equal to dy by du times du by dx, and this is the chain rule in what we call Leibniz's notation, because this d by dx notation or d by du notation, this is originally attributable to Leibniz. Now, as I said, this chain rule is fairly intuitive. It's very intuitive. It's very simple. And let us illustrate this with the help of an example from economics only. Now, in this example, we have set it up as follows. The quantity demanded, which is represented by x, the quantity demanded for a commodity x depends on price. So the quantity demanded is x, and that depends on price p. The price p is not constant, but it varies with time. So if we go by the chain rule, then our dx by dt, if we want to understand how the quantity demanded varies with respect to time, that by the chain rule would be given by dx by dp times dp by dt, because x changes with respect to p, and p is a function of t. So every time t changes, that will lead to a change in p, and every time that p changes, that will then cause a change in x. So by the chain rule, this is the formula that we have. Now let us give it more structure. Let us suppose, for instance, let us look, for example, at the quantity demanded of tomatoes. And let us suppose that the quantity demanded of tomatoes by a restaurant decreases by 50 kilos if the price goes up by 1 rupee per kilo. And suppose further that the price per kilo increases by 50 paise per week. The question here is, what is a decrease in the quantity demanded in kilos per week? Now, if you notice here, basically what we are saying is, whenever the price increases by 1 rupee, the quantity demanded falls by 50 kilos. So that's minus 50. So what this question is asking you is, if the price increases by 50 paise, which is 0.50, then what will be the decrease in the quantity demanded? And now you can see here by the unitary method, that's nothing but minus 50 times 0.50. But an alternative way of looking at things is actually to use a chain rule, because this minus 50, if we were to interpret these rates of change, what we have here, minus 50 or 0.50, these rates of change could be given the interpretation of derivatives. And if we take dx by dp approximately as minus 50, right, how quantity demanded changes with respect to price as minus 50 approximately, and if we take dp by dt as approximately 0.50, this is exactly what we have to calculate. This is exactly the calculation that we'll be doing to calculate dx by dt, which is nothing but the decrease in the quantity demanded per week. And that, as you can see here, would be 50 times 0.5, which is going to be 25 kilos. Also, we can look at the generalized power rule, which we developed in the first part of the lecture, as a special case of the chain rule. The generalized power rule said that when y is equal to g of x to the power a, that implies, here a is, let me just back up. So a here is a constant, it's an arbitrary real number, and g is a differentiable function of x. In this case, dy by dx, by the generalized power rule, we said, and this is based on the pattern that we developed, so that was not really a formal proof. So dy by dx, we said, was a times g of x to the power a minus 1 times g prime of x. Now, what we can do here is, let us suppose we put g of x as u, right? So in that case, our y will become u to the power a, because y is g of x to the power a. So if g of x is u, y becomes u to the power a. This is then to say that dy by dx is equal to a times g of x to the power a minus 1 by the generalized power rule times g prime of x. And this, because g of x is u, so that then becomes a times u to the power a minus 1, and g prime of x is nothing but du by dx. So if you notice here, this a times u to the power a minus 1, this is nothing but dy by du, because y is equal to u to the power a, we put g of x equal to u. So dy by du will be a times u to the power a minus 1, and that is then multiplied by du by dx. So dy by dx, as far as the chain rule is concerned, that is dy by du times du by dx, which is exactly the same calculation that we have done. So we can argue that the generalized power rule, it is a special case of the chain rule where in particular y is equal to u to the power a. And we will be, once we prove the chain rule formally, which is what we're going to do towards the end of this video, then you can just take the generalized power rule to be a special case of the chain rule straight away. Now let us look at a couple of examples to practice this chain rule. We have y equal to u to the power 4, and u equal to 5x cubed minus 1 in this particular example, part A. And you're asked to find dy by dx. So dy by dx by the chain rule will be equal to dy by du times du by dx. As you can see here, dy by du will be 4 times u cubed, and du by dx will be equal to 15x squared. So that you multiply. So to get dy by dx equal to 15 times 4 is 60, 60 times u cubed times x squared. But we have to put everything in terms of x because that is our base variable. So here u then can be written as 5x cubed minus 1, and that then gives us minus 60. That is 60 times x squared times 5x cubed minus 1 to the power 3. This is a typo here. So that'll be our dy by dx. Now let us suppose y is now given by 3 divided by x squared plus 5 the whole squared. So here we can put u equal to x squared plus 5, which then gives us y equal to 3 times u to the power minus 2. Okay. Now, if we again use the chain rule, dy by dx is dy by du times du by dx. dy by du is minus 6 times u to the power minus 3 using the power rule. Du by dx is 2 times x. So, if you substitute that in the formula for the chain rule, you're going to get minus 6 times u to the power minus 3 times 2x, which is then minus 12 times x divided by x squared plus 5 to the power 3. Now, we can also extend the chain rule and even apply it more than once. In particular, and this can be extended to as many functions. So let us suppose that y is a differentiable function of u, and u is a differentiable function of v, and v is a differentiable function of x. Then we can say that y is a differentiable function of x. Basically, you have y as a composite function of x again, which is where you're building a function which is a combination of different functions. And we can write dy by dx as dy by du times du by dv times dv by dx. Let us look at an example to illustrate this. So here we have that y is equal to under root 1 plus under root x plus under root x. What I have done here is that I have taken u as under root of x plus square root of x, and that then implies that y is equal to square root of 1 plus u. Now, u in turn can be written as square root of v, where v is equal to x plus root x. And now we are in a position to calculate dy by dx using the chain rule as dy by du times du by dv times dv by dx. Let us look at the calculations in detail. So y is equal to square root of 1 plus u. So this implies that dy by du is equal to half times 1 plus u to the power minus half. Now, u in turn is something we've written as square root of v. So, du by dv will be half times v to the power minus half. And v we have written as x plus root x, and dv by dx you can calculate to get x, the derivative of x, which is 1, plus the derivative of root x, which is half times x to the power minus half. Now, let us substitute all these three results into these three terms here for the chain rule. So, that will give us half times 1 plus u to the power minus half times v to the power minus half times 1 plus half x to the power minus half. And because we want to reduce everything to x, so we can substitute here because u is nothing but square root of x plus root x. And because we have a minus half here, I can take this entire term to the bottom in the denominator here. We have half times half, which is 1/4, which comes up front as a constant. So 1 plus u to the power minus half can be written as 1 divided by square root of 1 plus root x plus root x. and that is then multiplied by v to the power minus half, which is nothing but 1 divided by root x plus root x times 1 plus 1 by 2 times square root of x. So this is to illustrate how we can apply the chain rule even more than once or any number of times depending on the situation where this kind of a rule works. So it makes things quite tractable. Now let us look at an alternative formulation of the chain rule, which is very important, because what happens is that for the notation that we have just seen for the chain rule, which is the Leibniz's notation, there that is in terms of d by dx. But we might also want to specifically, explicitly state the point at which we want to evaluate the derivative, which is something we can do there also, but it's easier here. And let us formalize things. So again, if y is a function of u, where we're writing y as f of u, and u is a function of x, so that u is a function g of x, then we can write the notation as y equal to f of g of x. So this then allows us to explicitly write here the value of x at which we are evaluating the derivative. Now, if y is a function of u and u is a function of x, then y is equal to f of g of x. And here again, as you can see, y is a composite function of x. In particular, in this kind of a notation, where we write y as f of g of x, this function, we first compute g of x, which is called our kernel function. Kernel in English is the inner part of a seed, or when you have corn, the inside of the corn, so that is the kernel. So similarly, this is the inside part of the function. So you first compute g of x, which is our kernel, and then apply the function f to g of x. F here is the exterior function. That is how we look at a composite function. Now, the chain rule is stated as follows with this kind of notation. If the function g is differentiable at x naught and f is differentiable at u naught equal to g of x naught, then we can say that f of g of x naught is also differentiable at x naught, and the derivative, we are writing f of g of x naught as capital F of x, so capital F prime of x naught is then given as f prime of g of x naught times g prime of x naught. So f prime evaluated at g of x naught and g prime evaluated at x naught. Now, let us look at an example to illustrate this. So, let us suppose that capital F of x is f of g of x, and we want to calculate the derivative at x equal to minus 2 if f of u is equal to u cubed and g of x is equal to 1 minus x squared. So, here we have that f prime of u is equal to 3u squared and g prime of x is minus 2x. By the chain rule, f prime of x from the formula that we just developed is f prime, small f prime of g of x naught, our x naught here is minus 2, times g prime of x naught. So, f prime at minus 2 is equal to small f prime at g of minus 2 times g prime of minus 2. Now, g of minus 2 is nothing but 1 minus 4. Right? G of minus 2 is 1 minus 2 squared. So, that's 1 minus 4, that's minus 3. So, f prime evaluated at minus 3, which is g of minus 2, is going to be 3 times minus 3 squared. So, that's 9 times 3, which is 27. And further, we want g prime at minus 2. So, g prime at minus 2 is minus 2 times minus 2, which is 4. So, the derivative here at minus 2 is given by 27 times 4, which is 108. Now, just to speak a little bit about the notation, this notation f of g of x can also be written as f with this symbol in between f and g. And this is read as f of g or f compounded with g. This is a function that maps x to f of g of x. Similarly, the function that maps x to g of f of x is written as follows: g of f or g compounded with f, right? So f of g of x is nothing but this notation here at the bottom, and this is how we can write g of f of x as well, g compounded with f. These are just alternative notations. So let us just elaborate on this so that you get comfortable with the notation. So if I just pick up the expressions from the previous example, in the previous example, f of u was u cubed and g of x was 1 minus x squared. Now, if I ask you to find f of g of x, basically what am I doing in f of g of x? My input here is g of x, which is 1 minus x squared, and that is what I'm going to substitute for u here, which is the argument for f of for the f function. So that then gives me 1 minus x squared to the power 3, the whole to the power 3. And then g of f of x means that I have to put f of x as my input. Now, what is f of x? F of u is u cubed, so f of x would be x cubed, and that then gives us g of f of x as 1 minus, so instead of f of x, I'm going to put x cubed, the whole squared, and that then gives me 1 minus x to the power 6. So this is just to help you understand this notation, and this way, if you practice more questions, you can pick up questions from other books. You should be able to go both ways, whether it's f of g of x or g of f of x, and these are good questions for practice. Now we will now end this lecture with a proof of the chain rule. So this is something I've left for the end because one always wants to practice some questions also before, because for students one may not always want to get into heavy proofs. So I left it for the end, but nevertheless we are going to do it. Our chain rule works like this. So our capital F of x, which is a function in question, that is f of g of x, and we want to find the derivative of this function at x equal to x naught. Now, we're going to be again using the limit definition here. So, recall from earlier lectures that if I were to calculate the derivative of this function small f at x naught, the limit definition is given as the limit of f of x naught plus h minus f of x naught divided by h, the whole thing divided by h, as h tends to 0. So, if I write this, if I bring in the limit definitions again, now what I'm going to do is, here on this slide, actually I've given you the result, so that you get a sense of what you have to prove. Now, our function is f of g of x, which is capital F of x, and we have to prove that f prime at x naught is small f prime of g of x naught times g prime of x naught. Now, what I have given here is a result that you have to prove. So, what you might want to do is just write this down on a piece of paper or take a photograph and just keep it with you while I walk you through the proof, because this will give you a sense of why we are developing the proof in the way we are, right? Now, the small f prime of g of x naught can be written as a limit as h tends to 0. Now, because here the argument is g of x naught, so I can write here f of g of x naught plus h. So, instead of x naught on top, I have g of x naught plus h minus f of g of x naught. And that is then multiplied by g prime of x naught, which is the limit as h tends to 0 of g of x naught plus h minus g of x naught, the whole thing divided by h. Okay. So, this is what we have to prove. Now, so if I were to just develop this proof from the basic limit definition, we have our capital F function, which is a function of x, and I want to develop the derivative at the point x naught. So that is going to be given as a limit as h tends to 0, capital F of x naught plus h minus capital F of x naught divided by h. Now note here this Newton quotient, which is capital F of x naught plus h minus capital F of x naught, the whole thing divided by h, that can be written as f of g of x naught plus h, okay, instead of x I just write x naught plus h, minus f of g of x naught, and then the whole thing divided by h. What I have done here is I have multiplied this whole expression, which is a Newton quotient. I've multiplied and divided it by this number k, where k is equal to g of x naught plus h minus g of x naught. So k is basically telling me how the function g changes, by how much the function g changes when x changes from x naught to x naught plus h. Now, why have I done this? I want to somehow bring in this g of x naught plus h minus g of x naught, because if you go back to the previous slide, so here if you look at the result that we had to develop, I already have this g of x naught plus h minus g of x naught which I want in the result. So that is why I'm bringing this into the picture. And now when I do that, I have g of x naught plus h minus g of x naught in the numerator and the denominator. So I haven't changed anything. But notice here that because I also want g of x naught in brackets plus h outside the brackets, I can also work with this formula to get g of x naught plus h as g of x naught plus k, right? So let us look at things here. This Newton quotient, if I look at the way I have modified it, this can be written as f of, because g of x naught plus h is g of x naught plus k. So g of x naught plus k minus f of g of x naught. Now what I've done is, instead of the h that I had at the bottom, I've brought in the k just to make it consistent with the k in the numerator. And notice here that as h tends to 0, k will also tend to 0. So that then allows me to take the derivative also. And then I have a k divided by h here. So that is nothing but g of x naught plus h minus g of x naught, the whole thing divided by h. Now notice here, once I take the limits, here the first expression would be nothing but f prime of small f prime of g of x naught as k tends to 0, which is exactly the first part of the result that I had asked you to take a picture of. And the second expression here is nothing but g prime of x naught as h tends to 0. So this is exactly the result that we were trying to get for the chain rule. And this is precisely the proof. So this is actually a very good proof to understand how the chain rule works. And with this, we conclude the second part of the lecture today. I hope you found this lecture useful. In the next video, we will be talking about other techniques of differentiation like implicit differentiation. We're going to be talking about linear, quadratic and higher order, higher degree approximations to functions. And we'll also bring in elasticity. So there's lots more to come. Stay connected and thank you so much for watching.